A multimeter is an electronic instrument that can be used to measure voltage, current, and resistance. Some multimeters can also measure frequency, capacitance, transistor parameters, and even temperature. Common multimeters are handheld devices that are useful in the field for basic fault finding and electrical equipment. Multimeters are available in analog and digital formats. Analog multimeters display their readings using a microammeter with a moving pointer. The lack of precision of analog multimeters have made these devices mostly obsolete. Digital multimeters, which is what we use in our lab, with their numeric displays are far more common due to their high degree of accuracy and low cost. Digital multimeters are commonly referred to as DMMs or VOMs. VOM is short for volt-ohm milliammeter. Available DMMs range from simple handheld devices that cost around $5 to wall-powered, benchtop, high-accuracy DMMs that cost thousands of dollars. Most teaching labs will be equipped with modestly accurate battery-powered DMMs costing in the range of $50 to $100. Let's briefly just cover what all the main symbols stand for, and then we'll go over their meaning and function later. The yellow button is the power button. In other words, it's the on and off button. The blue button is what's called the hold button. If you press the blue button, the reading will be held and frozen on the display. That can be very useful if you need some time to write down a measurement, but it can also be a source of concern and frustration if you don't realize the hold button is on. You might be trying to take a measurement and not getting any reading. That makes sense, and it might be because the hold button has been pressed accidentally or by somebody else. So make sure you don't have the black H on the display when you're trying to make measurements. The black H means the hold feature has been activated. On the dial, let's go clockwise from the top. The big dial is the most important control on the digital multimeter. It's divided up into segments or sectors, if you will, and those sectors are indicated by the letter markings on the outside. Degree F. This is for degrees Fahrenheit. You can measure the temperature with a special probe. HFE is an abbreviation. It stands for Hybrid Parameter Forward Current Gain Common Emitter, and it is used to measure the DC gain of a junction transistor. V with the wavy line or tilde to the right of it is for measuring AC voltage. V with the straight line and dots above it is for measuring DC voltage. A with the wavy line or tilde to the right of the A is short for amps. This is for measuring AC current. Amps is the unit of measurement for current. A with the straight line and dots to the right of it is short for amps. This is for measuring DC current. Hz. This setting is for measuring frequency. Hz is short for hertz, the unit of measurement for frequency. The musical note and diode symbol. This setting is for continuity. You use this setting to see if you have connectivity in a wire or circuit. Omega. This setting is for measuring resistance. The capital Omega symbol is the unit of measurement for resistance. When used to describe resistance, you pronounce this symbol as ohms. F with the weird symbol to the left of it, well, that weird symbol is the symbol for a capacitor. This setting is for measuring capacitance. F is short for farad, the units of measurement for capacitance. Now let's look at the ports left to right. A. You use this port with the letter A above it to measure large amounts of current. Again, A is short for amps, the unit of measurement for current. MA. You use the port with the letters MA above it to measure small amounts of current. MA is short for milliamps. HZV omega. The port with HZV omega above it is used for measuring frequency in hertz, voltage in volts, and resistance in ohms. COM. COM is short for common. You can think of this port as being used for your ground connection. The screen is set to display your measurements. Your screen will change depending on where your dial is set. We will talk about the screen more with each different setting. These are all the features or settings that you'll be using for this experiment. For this lab, we will be using the ports labeled HZ, V, Omega, and COM. We will also be using the dial settings labeled V for DC voltage and Omega for measuring resistance. Now we'll cover the ports we'll be using for this lab. The first one is labeled COM, which stands for common, which we would also refer to this connection as ground. So that is where you normally plug in the black lead to the black connector. The next one over is for most everything else, HC omega. You use this port for measuring frequency in hertz, voltage in volts, and resistance in ohms. The red plug plugs into this port. Alright, so we're going to insert the probes into the digital multimeter. The black probe goes into the jack labeled COM for common or ground. The red probe goes into the one right next to it labeled HC omega. Now we can select what we want to measure using the dial. So now what we're going to do is we're going to demonstrate the continuity checker. We can turn the dial to the musical note and diode symbol. You use this setting to see if you have connectivity in a wire or circuit. When the probes experience a connected wire or connection through a circuit, or if we connect them directly to each other, we'll get a tone. This is very handy. It means that you don't have to look over the display while you're checking the circuit. V with the straight line and dots above it is for measuring DC voltage. The settings that we're going to be using and talking about are from here to here. There are 5 different ranges that you can select, ranging from 200 millivolts to 1000 volts. For this lab, we won't be using the higher voltage branches. We will just be using the 20 volts or the 2 volt setting. Let's use the digital multimeter to measure the voltage of this 9 volt battery. It's 9 volts in name only. Most 9 volt batteries have more than 9 volts when they're fresh, less voltage after they've been used for a while. But they're right about 9 volts, and they have a plus and a minus symbol for positive and negative terminals. They're usually marked on the battery case of a 9 volt battery. Normally the smaller terminal is positive and the larger terminal is negative, but it's marked on the case. And I have it set on the 20 volt setting because I'm about to try to measure the voltage of a 9 volt battery. 20 volts should give me the most precision that I can hope for, so I'm going to connect the leads to the battery, and that will give me a reading. So I now read 9.49 volts. Now I try to measure in the 200 volt range. I get a valid reading, but I lose a decimal point of precision, so it's reading just 9.4. You can see I'm only getting 2 significant digits. What would happen if I tried to measure the 9 volt battery at the 2 volt range? Trying to measure the 9 volt battery on 2 volt range gives you an overload. That's what the 1 with a decimal point on your display means. It won't hurt the meter, but it's just telling you that it can't read this much voltage on that low voltage setting. And then, just for fun, what I can do is reverse the probes. Maybe I didn't know which one was positive and which one is negative. You won't hurt a thing. What you will get is a negative sign in front of your voltage reading. That is just telling you that your probes are reversed. The other sector of the dial that we'll be using is for measuring resistance, and that is indicated by the capital Greek letter omega. First thing I always do when I'm measuring the resistance is I connect the bare leads together to make sure I get close to 0. So that's like balancing a scale before you make a weight measurement. You want to make sure it's zeroed out. So we have 0. Now this particular meter has a power saving feature that turns off the display after a certain amount of time, so I had to turn it back on. And you have to know what scale you need to get the correct measurement. And that also has 5 ranges, ranging from 200 ohms all the way up to 20 mega ohms. Most of the time we'll be using 20 kilo ohms or less, but you might have occasion to use up to the 2 mega ohm range. So we're going to select the range that matches the resistance we're trying to measure. Another way of thinking about finding the correct selection on the dial is you are trying to get the best precision. Let's say, for example, you select 200. That means anything over 200 ohms will read an overload, like what's shown here. And if you select the 2K, which K stands for 1000, so this is the 2000 ohm setting, if the resistance is anything over 2000 ohms, you will get an overload reading. For example, if we're trying to measure a 1000 ohm resistor, we suspect that it's in the range that is larger than our expected value, and that's so you can get the most precision. I'm going to connect these probes across a 1000 ohm resistor, and you can see that we do get a reading, and it's a valid steady reading. So if I were to increase the range setting to 20K, what happens is that I'd lose 1 digit of precision. So now it's rounding off to 0.97. If I were to continue increasing the range setting, I would lose more digits of precision. If I were to use the 20 mega ohm range to measure a 1000 ohm resistor, it would barely even show up in the last decimal place of the display, so I would lose accuracy. I need the lowest range setting that gives me a valid reading That is not an overload condition. That way I will get the most precision. Now you might wonder what to do if you don't have any idea what the resistance value is. In that case, what you want to do is start at the lowest range. If you get the 1 with a decimal point after it, that's telling you that the resistance you're trying to measure is larger than that range value allows. So you go up to the next highest range, see if you're getting a reading, and so forth. You continue all the way up the scale until you get a valid reading. A resistor is not polarized. That means it doesn't have a plus or minus. So it doesn't matter which probe we put where. I'm going to put the probes on each side of the resistor and wait a few moments for it to settle out. As I said earlier, I'm reading about 0.974, but that's on the 1 kilo ohm range, so again that is 974 ohms. And just to show that it's non-polarized, I will flip the leads around. And you can see I get the exact same reading. So that's how we measure resistance. If you want to know more about the multimeter, keep watching. We are about to briefly cover the other sectors of the multimeter, but you will not be using these settings for your experiment. It might be good to familiarize yourself with them. It might help you in the future, plus you will know what not to do for this experiment. Degree F is for Fahrenheit. You can take temperature with a special probe. You can measure temperature. There's a temperature probe that you can purchase separately for this meter. So there's a single range for degrees Fahrenheit. HFE is an abbreviation. It stands for Hybrid Parameter Forward Current Gain, Common Emitter, and it is used to measure the DC gain of a junction transistor. And then with another separate special probe, you can measure some transistor parameters. That's transistor gain. V with the tilde or squiggly line beside it. This is for AC voltage. Every digital multimeter has different measurement capabilities. This particular one, besides DC voltage and resistance that we've already looked at, has the ability to measure AC voltage. There's a whole sector for measuring AC voltage, so if you are working on wiring in a building or home, you might need to use this setting. This sector will allow you to measure all the way up to 750 volts AC. Then there's a sector for measuring both AC current and DC current. A with the wavy line or tilde to the right of the A is short for amps. This is for measuring AC current. Amps is the unit of measurement for current. A with the straight line and dots to the right of it is short for amps. This is for measuring DC current. So you can measure DC current and AC current, but you have to use different jacks on this instrument. There's a whole specialized technique for measuring current that we're not going to explore here, but that's what this range is for. HC, this setting is for measuring frequency. HC is short for hertz, the unit of measurement for frequency. It can measure the frequency of an AC signal, and that's down here where it says 2K and 20K. F with the weird symbol to the left of it. Well, that weird symbol is the symbol for a capacitor. This setting is for measuring capacitance. F is short for farad, the units of measurement for capacitance. And so there are 3 capacitance ranges. Other ports not used in this experiment. MA, you use this port to measure small amounts of current. MA is short for milliamps. This jack is physically the same size as the other probe for measuring current, but this one is intended for measuring smaller amounts of current. The port that's labeled milliamps does have a fuse in it, and that is to protect the instrument from getting excessive current and still being able to read with precision. If the current is too large, you can blow a fuse. And the next one over from that is for measuring larger amounts of current. The port with a capital A. You use this port to measure large amounts of current. Again, A is short for amps, the unit of measurement for current. The reason there are 2 different jacks for current is the one for measuring large amounts of current is actually unfused, and that's printed on the case. The reason for that is so that you can measure a lot of current without having to worry about blowing the fuse on the instrument. However, there is a limitation, and that's marked on here. It says 20 amps max for 10 seconds. And if you exceed that, you may cause damage to the instrument.